All right, here's the first part to the review for our first chapter test. So this review was made by a different teacher, and I stole it. So there are going to be some questions, particularly the first three that we have seen before in class. I still want to go over them because I want you guys to realize that you just need to read the word or read the problem and look for some keywords as you do this. So, throwing a ball up into the air, the ball reaches a maximum height. Maximum height means that when I look, there will be a high point compared to all of these other low points in my graph. And then once we figure it out, we label our graph height of the ball in seconds since the ball was released. So I'm just going to start with the labeling. This is situation 1 because I clearly have a high point compared to the points around it. All right. Number 2, every living thing has a constant amount of carbon-14 in it. This constant is not meaning this. This is, we all have carbon-14 in our bodies right now, and while we're alive, we're going to maintain that same amount. So that's all that constant is using for this situation. The carbon-14 begins to decay. So there's exponential decay as soon as the organism dies, such that half of the carbon-14 decays every 5,730 years. So we're going to see, it's going to decay by half, then half, then half. So, when it's changing by a half like that, that's exponential growth or decay. So this is situation number 2. And then I'm going to label in just a moment. And then our final one, Jenny's flying the plane at a cruising altitude of 8,000 feet. So that's where this graph comes into place because this is where she starts her descent, as they mentioned in a little bit. She begins her descent, so it's going down at a constant rate. So this word constant has a rate of 500 feet per minute. And so if we actually followed the slope, we would see it's going down about 1,000 feet every 2 minutes. That would probably be the easiest. So here's 1,000 feet, 2 minutes, 1,000 feet, 2 minutes. And then again, I would label my graph in just a moment. So this is situation number 3. So once I'm done and they asked me to label, I did that here. So height of the ball, seconds since ball is released, time is the x-axis, minutes since descent, altitude in feet, years since organism dies, and then the amount of C14 remaining. So again, any time is an x-axis. So from there, we got to answer some questions. So based on the different questions, we go to a different graph. So what's the y-intercept on graph B? And explain what the point represents in context to the situation. So I'm going to be going back and forth for my written answers to this, so you'll want to pause if you need to write these answers down. So the y-intercept on graph B, right here, is 8,000. And it's not enough that you write 8,000. You have to write what it means. So what I wrote is the y-intercept of 8,000 represents the height of the plane when she began her descent. So don't just say 8,000. Explain what it means in context of the situation. So we're looking for complete answers. All right. The next problem. So what is this says f of 2 in graph A. So when I go to graph A, what this means is if x is 2, it wants to know what's y. And then we have to explain what it means in context of the situation. So when I go to x is 2 and I go up here, we're talking about this point. So again, here's my answer, x equals 2. So when x equals 2, it means 2 seconds after the ball was released, the ball was 90 feet in the air. So again, don't just say 90. Explain how 2 gets you to 90 and what the 2 mean. All right, the next one, number 6. What is f of 12 in graph B? So again, this just means if x equals 12, this is something learned in Algebra 1, what's y? So I'm going to go to graph B. So when x is 12, here we go, I get y to be 2,000. So x equals 12. 12 minutes after the descent began, here we go, the plane is 2,000 feet in the air. That's what that means. Again, complete sentences. Don't just say 2,000. 12 gets you to 2,000. Explain both of them. And then the final one, what x values, makes sense for graph C? So what x values? I don't need this whole graph. And so I'm actually going to go to my labeled graph. So this is years since the organism dies. I actually don't need this part because I'm not going to have negative time. So I'm looking for my graph from here and beyond. Okay, so I'm looking when, let's see if we can focus that, when x is 0 and bigger than 0. So I wrote values where x is greater than 0 makes sense. You wouldn't have negative time. So something like that, all right? Okay, let's go to the next page. Sorry. All right, the next part was from your pink transformation packet, and it's just all the different shapes and putting names to them. So I already did this, I don't want to rewrite it again, so I'm just going to show what I have. And I'm putting them in a certain order because this is the order of how we go through it during the school year, but you can have these in any order. So, you know, you've got linear, any of these pictures work, absolute value, you could have this, or you could have this, quadratic, you could have regular, you could have upside down. You have cubic, this is the traditional cubic, but it could also go like that. And on the mile marker, you actually might see this as well as the test. So just understand both of these shapes. Square root has a starting point and then an arrow. This is the only one that doesn't have arrows on both ends, but could also flip. And when things are flipping, I hope everything that we're going to do is going to flip over the x-axis. So that flips to here, just like the absolute value flips over the x-axis. Same with the quadratic. Even on the cubic, this dark part flips to this red part, and this dark part flips to this red part. Cube root, a little flatter than cubic. Again, this is the more traditional one, but you also might see this shape. Exponential, just looking, this is the only exponential shape you're going to see. So, and you should recognize that one, exponential growth. Here's logarithmic. So this kind of looks like a lowercase r, where this looks like a backwards L. Your rational inverse, the dark ones are the original, but again, this could flip down to here, and this one could flip up to here. So the red wavy ones might work as well. Your step function, and again, don't draw this part of the step, just this, because if you draw this, you're having x values repeat, and in a function, x doesn't repeat, so no stacking like that. And then periodic, and I actually should have my arrows on that, just some type of wave. All right? Okay, next couple questions are multiple choice. Let's go through those. So now that you have those, you can answer these questions. This is periodic, so it's C. Next page, again, and what this should have is an arrow here, so this is not very good as far as the picture goes, but it has a starting point and it keeps going. This is our square root. The graph to the right, this is exponential growth. So remember, exponential looks like a backwards L, or decay, then it could look like a regular L. The graph to the right is a function. Let's see, this is the cube root. And then this is your log shape. There should be arrows there. So this is our log shape. And on the mile marker and on the test, I will make sure that there are arrows, but that's your log shape. And then the last one, this is actually called a piecewise function. This will not be on your test. It is not on the mile marker, but it's just pieces of different functions. So they call it a piecewise function. All right? All right, next ones. You have to sketch a quadratic with two real roots. So roots, x-intercepts, zeros mean the same thing. So I want to see a parabola that crosses the x-axis twice. So it can be regular. It can be upside down. It doesn't have to be perfect. But I believe on the test they're actually going to want the coordinates as well. So pick something simple and then draw your U. Well, it's supposed to go through there. So I have at -2, 0 and at 2, 0. One real root means it's only going to touch the x-axis once. So pick your point and then draw it. So -1, 0. And then no real roots. So when you draw your parabola, you don't want it to touch the x-axis. It can touch the y-axis, but not the x-axis. So that's one possibility. All right, now you need to sketch an exponential with the y-intercept of 0, 1, and a growth rate of 2. So this is a good time to make a table. And we already got 0, 1, and a growth rate of 2, that's a 1, not my y. means that as my x's increase, my y's will increase by multiplying by 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and then just get as many points as you possibly can on your graph. So I already have the 0, 1. Here's 1, 2, 2, 4, 3, 8. And remember, you guys, exponential growth and decay have a, it's not supposed to be crossing, like that wall. So make sure it looks flat and then grows really fast, okay? So now, same, y-intercept to 0, 1, but this time it's going to have a growth rate of 1/2. So when I did this one, a growth rate of 1/2 means it's going to get smaller as I go through. So I actually started with smaller values and then worked my way. So watch, I'll show you. So basically, here's my y-intercept. I took half of some number to get to 1, and that was 2. And I took half of some number to get to 2, and that was 4. And half of some number to get to 4, and that's 8. Now I can take half of 1 if I want, and I can take half of 1/2. But those points are going to be a little bit tougher to graph. So I'm just going to graph my non-fraction numbers, my integers. So there's 0, 1. Here is -2, 4. -3, 8. Whoops, I messed up on that one, sorry. -1, 2, ignore that one. -2, 4, and -3, 8. And then I'm going to have that decay shape. And again, let it flatten out to clearly show that wall, or that asymptote. And then finally, growth rate of 3. We've already had that. Same y-intercept, 0, 1. Make your table. And then as x gets bigger, my y's are multiplying by 3. So times 3, times 3, and I'll just get a few more points on there then. So 1, 3, and 2, 9. And again, draw that asymptote, draw that wall, draw that flattening out, and then it goes up. Okay? So we had this one already. All right, let's go to the next problem. I need to sketch a linear function. This is review. I've got a y-intercept of 2, and I got a negative slope, so it's going downhill. And this is my rise, this is my run. Rise over run. So I'm going to rise 2 and go over 3, or I could go down 2 and then to the right 3. Just get enough points so that you can make your straight line, and then don't forget your arrows. Y-intercept of -3. This is a slope of 2. It's positive. It's going uphill. I need a rise over a run, so I'm going to rise 2, run 1. Up 2, over 1. And just make sure that when you're done, your line is going the correct slope direction. Okay? And finally, 0, 0. Slope is 1/2. It's going uphill. My rise is 1, my run is 2, so up 1 over 2, up 1 over 2, down 1 over 2. That's good. And then again, don't forget your arrows. All right, let's get this last part, and then I'm going to stop the video and you can go to the second part of the video. So use the tables to identify the graph. So the x's are going up by 1s on the first 2. So just how do we go from 1/2 to 1, 1 to 1.5, 1.5 to 2? I'm always adding 1/2. So that means since I'm adding the same amount, it's linear. Again, the x's are going up by 1, so how do we go from 4 to 1, 1 to 0, 0 to 1? Here I'm subtracting 3, here I'm subtracting 1, now I'm adding 1, so it's not linear. Is it exponential? I'm just going to pick some y values and divide it by the previous y value. So 1 divided by 4, 0 divided by 1, 1 divided by 0. If this were exponential, then these 3 fractions, for instance, should be worth the same amount. And they aren't, so it's not exponential. So now I'm going to check for quadratic. So to go from -3 to -1, I add 2. To go from -1 up to 1, I add 2. And to go up from 1 to 3, I add 2. So this one is quadratic. And the last one. So how do I go from 2.1 to 1.8? I subtract 0.3. Here I add 0.1. Here I subtract 0.3. Here I add 0.2. That's definitely not linear. If I start dividing these fractions, so 1.8 divided by 2.1, 1.9 divided by 1.8, I'm not going to get the same amount. So as it turns out, this is not exponential, and there's no consistent pattern from here to here, so it's not quadratic. It's neither.